It's again the same class 1B, lecture 1 part 2, because we cannot put too many things, it takes too much time to get uploaded. So, starting with what we have spoken about, the angle between two the inner product between two vectors. Here we are going to talk about angle between two vectors. As you will see very beautifully, the notion of angle between two vectors is linked with the notion of inner product. So, so what's happened is that let us see how we can start looking at this issue. Now, suppose I have an inner product of two vectors which gives me 0. So, what do we mean by this? What is the scenario? One can have something have 0? Suppose I have a vector x y as coordinate x y. Suppose I have another vector which has coordinate minus x and minus y. So, then what would be the inner product, right? So, suppose suppose I have a coordinate, I have a point with coordinate x y. So, so that is a vector v. So, what should I choose a vector w, so that the product would become actually 0, right. So, now suppose I have minus y and x as w. So, if I multiply this, if I take the inner product of these two, then I will have minus x y plus x y as the inner product, which will give me 0. So, let us look at what is the meaning of in place of x I have minus y. So, what I had as y, that would come in now place of x, and and x takes the position of y. So, if you draw that thing on your take a vector, say 1 1, and then take the another vector as minus 1 1. So, where is minus 1 1? So, x is now minus 1. So, if you are 1 1, you are making a 45-degree angle with the x axis, and since 45-degree angle with the y axis, that particular line joining 0 0 with 1 1. And then if you are minus 1 1, minus 1 1 also has an angle of 45-degree, that line, the point minus 1 1, when it is joined with the x axis line, the origin, then it also has with x axis 45 degrees, and also with y also with 45 degrees from the y axis. If you go up, x axis, if you go up, you have 45 degrees, but it also has 45 degrees from the y axis. So, the internal angle between these two vectors is 90 degrees. So, it is important to think that possibly if I have u and v, two geometrical vectors, say in R2 or R3, which is whose inner product is 0, they might be perpendicular to each other, that is, the angle between them is 90 degrees. So, how would you think of doing it? Let us try to compute norm of u minus v square. Always observe, if u is the side of a triangle and v is the another side of a triangle, a vector representing. So, if one side of a triangle is represented by the vector v, that is, and its length hence is norm u, and another side is represented by a vector, say u, whose length is norm u, then the third side is represented, can be represented by the vector u plus v with norm u plus v. So, let us see, but if norm u plus b whole square, that is c square, is equal to a square plus b square, then it must be a right angle triangle. That is essentially the converse of the Pythagoras idea, and that is apparent if you do try to compute the norm of u plus v. So, norm of u plus v whole square is the inner product of u plus v with u plus v. So, again you apply u plus v is now first taken with u. So, this is now fixed, thought of as one vector. So, this is like a w inner product u plus v, w into u plus w into v. So, now again here you are writing in the same way, it will apply the inner product rules, it will be inner product u with inner product u, vu plus uv plus vv. So, norm u square plus norm v square. Okay. So, because uv equal to 0, because I have already assumed that, which means now one square of one side is sum of the square of two others. So, it must be the angle between u and v, the angle between the sides represented by the vector u and v must be 90 degrees, for example here. So, this is the diagram. So, orthogonality of two vectors means they are called orthogonal. When two vectors are 90 degree, they are called orthogonal, and this is a very important concept. Now, how do I link? So, I have been able to link the inner product with orthogonality, and that when the angle is 90 degrees, I now know that u intersection u v should be equal to 0, right. Now, because if the angle is 90 degrees, what would happen? If the angle is 90 degrees, again you go back to this, you will have this thing, u norm u square plus norm v square plus 2 norm u v. Now, because it's 90 degree by Pythagoras, norm mu plus v whole square is equal to norm mu square plus norm v square. So, this will cancel, giving me 2 norm u v equal to 0. So, u v equal to 0, hence that is what I needed, that if the angle between the two sides is 90 degree, two vectors u and v is 90 degree, the inner product must be 0, and vice versa, both ways. So, now how do I link the angle between any two vectors which need not be 90 degree and the inner product between them? Gilbert's triangle gives a very beautiful approach to it, and I do not see that being done by anybody else. So, he takes the row vector form of u. So, basically u equal to 1 0 transpose means u is actually 1 0, instead of writing as a column vector for space, I have written it as a row vector. Now, you take the vector 1 0 on the line and consider a circle of radius 1 centered at 0. So, 1 0 is also on the circumference of the circle. Now, given the theta, any point here, any xy point here, x would be equal to 1 cos theta, and y could be equal to cos theta, r cos theta and r sin theta, but r here is 1. So, it is cos theta and sin theta. Now, you take the inner product of these two vectors u and v, they are of course unit vectors, because here norm v square is cos square theta plus sin square theta, which is 1. So, if you take the inner product, you will have cos 1 into cos theta plus 0 into sin theta, which will give you cos theta. So, which means that if I take any two unit vectors, maybe in Rn, this possibly might be true. Let us make that intuitive jump. Sometimes in mathematics you have to make intuitive jumps, some leaps in the imagination, later on you can go and prove in a more detailed way. So, is it true for any two unit vectors? Here I have chosen u very specifically, where theta is 0, then cos theta is 1 and sin theta is 0. Now, suppose I do not do so, and I take two unit vectors in R2. Actually, what I have seen is in R2, here instead of Rn I should have written R2. So, I take two vectors in R2. So, one given by which is making an angle theta 1. So, u making an angle theta 1 with the x axis, v making an angle theta 2 with the x axis. So, u is cos theta 1 sin theta 1, of course, that is the coordinate, and v is cos theta 2 sin theta 2, of course. So, that is a kind of representation in what you can say polar coordinates r theta. I assume that you know this basic coordinate geometry. Now, what would happen, because x is r cos theta, y is r sin theta, this is called polar coordinate representation. Now, what would happen, the angle between these two u and v, which is theta 1 minus theta 2, and let us see what is cos theta. Cos theta is cos theta 1 minus theta 2, which you know from basic trigonometry is cos theta 1 into cos theta 2 plus sin theta 1 into sin theta 2, and that is nothing but the inner product cos theta 1 into cos theta 2 plus sin theta 1 into sin theta 2. That is nothing but the inner product between u and v. So, for any vector in R2, I can any unit vector in R2, I can always write cos theta is u into the inner product between u and v. So, we are through. So, let us just stretch the imagination and say for any vector, two vector unit vectors in Rn, that is the vectors with norm mu equal to 1 and norm v equal to 1, if theta be the angle between them, then cos theta is equal to u inner product v. Now, what happens if cos theta and theta is angle between any a vector of two vectors of some given length, need not be the unit vector. So, you can now construct out of a given vector u and a given vector v, you can construct two unit vectors by dividing them by their norm, basically 1 by norm mu, assuming that these are non-zero vectors. If one of the vectors is 0 vector, then obviously the inner product is 0. So, you know that angle is. So, the one of them is a 0 vector. So, anyway u v equal to 0 and cos theta theta should be 90, and obviously because cos theta is 0 and cos, but of course that is very strange, because if one vector is 0, what is the meaning of having angle 90 degree? There is essentially no angle, that's vacuously taken to be 90 degree. So, we are talking about vectors where we really work with, they are non-zero. So, if u and v are two non-zero vectors, then we can always get out of those two non-zero vectors two unit vectors. One is u hat, which is u by norm u, one is v hat, which is v by norm v, because norm u and norm v are non-zero, because they are non-zero vectors. So, 1 by norm u is a scalar that you multiply with u, and 1 by norm v is a scalar that you multiply with the vector v, to scalar multiply. So, now if you take the norm of u hat, this will be norm of, actually what happens here, I need a property of the norm. Why? That is what we have not discussed. Say norm, what you happen, if you have scaled a vector by say lambda v, and then you want to calculate the length of it, and say lambda is a positive number, in this case it is a positive number, then the length is nothing but lambda times the norm of v, that I have only increased the length by lambda times, that I have stretched the vector lambda times or shrunk the vector lambda times, whatever, when lambda is strictly bigger than 0. So, these are unit vectors, vectors of norm 1. In fact, you can directly calculate it out, it does not matter. You can directly calculate out the norm and you will see that the norm would come to 1, even if you do not know the properties of the norms or think in this particular way. So, if theta be the angle between u and v, the key idea is to notice that if you have an vector u and you have a vector v, and then you have scaled them by 1 by norm u and 1 by norm v, that the new vectors that you have formed u hat and v hat would lie along the vectors u and v itself, that is they lie along the same direction, and hence the angle between u and v, if it is theta, the angle between u hat and v hat is also theta. And then I know that cos theta is u hat into v hat, that is already known to us, and hence if I write u hat as u by norm u, v by norm v, then applying 2 times the result which you already know for inner products, which is this result, let me show you, which is this result. So, then what you can do now is that you can bring out 1 by norm u out and 1 by norm v out, and you can write cos theta is u v, inner product u and v divided by norm u into norm v, and norm u v is norm u into norm v into cos theta. It is a very interesting way to talk about inner products and linking the angle between the two vectors with kind of. So, since mod of cos theta is less than equal to 1, I am very sorry, I seem to make a lot of typos, and I would request my students to forgive me, and please any viewer in fact can just remind me of my typos. So, it is mod of cos theta is less than equal to 1, and that would, if that is true, because mod of, if you, so now if you take a mod, so these are mod of this is actually mod of this into mod of cos theta. So, absolute value of cos theta, but this is anyway non-negative number, norm mu into norm v. So, it is the mod is not, is just forgotten. So, mod of cos theta is anyway less than equal to 1. So, this is what we get, norm mu into norm v is less than norm mu norm v. So, this is the Cauchy-Schwarz inequality. So, you see how beautifully, if you know how to get the link between the, if you want to can prove that if theta is angle between two unit vectors, and if norm u into norm, if u into v, the inner product is equal to cos theta. Once you know that, everything then follows, including the Cauchy-Schwarz inequality. Okay, there is some other way also to prove Cauchy-Schwarz inequality. So, Gilbert Strang in his 2020 book called Linear Algebra for Everyone actually also provides a very simple way to use the Cauchy-Schwarz inequality to prove the AM-GM inequality. I will not go into it, and it will be too much of details here, but you can understand it. It is not a very big thing. Just I keep it for you, for those who would read the notes, and but those who are seeing, maybe those who are not in IIT Kanpur, they would see the trick here, that V equal to A by B, U equal to A by B, and V equal to B by A. And so, I think anybody can ask me for the notes, I can just, one can see it. So, if I hold it for 2 minutes, anybody in love with mathematics will immediately understand what has been done. It is an application of Cauchy-Schwarz inequality. Okay, norm mu is this and norm v is this, and so okay, because actually AM-GM holds for basically non-negative numbers. You can assume A and B to be non-negative, right? It is a kind of AM-GM inequality. Because if one is non-negative and another, then it is obvious basically this side is positive. But if both are positive, then this happens. Now, you can use the Cauchy-Schwarz inequality to prove the triangle inequality. This is a problem I have left open, and actually I think in one of my, if you look at my series of YouTube lectures, and in one of my lectures this is actually done. If you see the list of lectures, I am telling my class students also, please go to the channel and see that, because there is a lot of stuff in the channel. If you want to brush up some of your math, you can just do it. Now, you take a detour. What do you mean by inner product of two complex vectors, two elements in Cn? Now, we are in a different territory. The game completely changes. That other territory looked comfortable, while this territory might not look comfortable, but it looks something. So, instead of transpose, there is something called a Hermitian. So, I just do not write a row vector, I write a column, what is called a conjugate transpose vector. Means what I do, if V is a vector in C and if Z1, Z2, Zn are n complex numbers as its component, then V star, which is called the Hermitian, is equal to Z1 bar dot 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 Zn bar. Means I first take the, I construct first the conjugate, a vector with conjugates of Z1, Z2, Zn, and then take a transpose of it, make it a row. Now, of course, Z conjugate means here that if Zi is xi plus iy, Zi bar is xi minus iy. This is where I is root over minus 1, and Z equal, if Z is equal to x plus iy, Z bar is x square plus y square, which is the length of the which is called the modulus of the complex number, which is length of the vector joining 0 0 to the point x plus iy. Now, so here a complex plane C is structurally the same as the plane R2, though they are functionally different, because here we are using complex number, here we have coordinates with real numbers. One might say, oh, they are same thing, just throw away x y and write x plus y, it looks like that. So, structurally same, but functionally different. These are called isomorphic structures, or so they have a bijective map from one point to another. to corresponding to every pair of numbers x, y, there is a complex number z equal to x plus I y. So, the how do I define the length? The length is actually v star v, inner product basically, kind of a complex inner product. So, the complex inner product would be basically z 1 bar or z 1 bar, whatever, whichever way you want to define it. So, so it is z 1 bar. So, if you write v star is this, and v is the column vector here z 1, z 2, z n, and then just like you do inner product, you do z 1 bar, z 1, z n bar, z n. So, it is trying to imitate the thing what you know in case of, so it this won't be v star dot v, this is a mistake, it will be just v star v. So, this is also you can use it as a complex inner product, you can write C like this or whatever. So, this definition, suppose I had not taken the conjugate, what would have happened? If I had not taken the conjugate, basically this would become z 1 square plus dot 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 z n squared. So, that will be a sum of some complex numbers. So, the norm square would become a complex number. So, but lengths are not complex numbers, lengths are real numbers, and that is why you have to take this conjugate structure, and that is why the notion of Hermitian comes into play, that you do not just take a transpose, but you take a conjugate transpose. So, there are a lot of interesting things in this whole issue. So, if I you can define the inner product, here I am making a mistake, it should be just w star v, not w star dot v. Actually, it looks like as if I am taking an inner product of w star with the vector v as I do for real, but it is better to write it as w star v. So, let us, I have asked you to think why the complex inner product is defined in this way, I have just given you the answer. So, here it is. Now, in general, if it is defined in this way, so that when I compute the length of the vector, it gives me a real number. So, here if you look at the inner product, I have a vector w where these w1, wn, these are complex numbers, I have taken their conjugates. So, they are also complex numbers. So, this product, this number is a complex number, not a real number. So, if you take two vectors in Cn and take their inner product, that must be a complex number. So, inner products are mappings which picks up two elements from the vector space and returns them to the field on which the vector space is defined. That is a very erudite way of talking about inner product, but here we are in Cn, take two vectors, if I make the inner product, I want them to be in C, in the space of complex numbers, because complex numbers are the scalars that we use to study this vector space Cn. I have not yet formally defined what is a vector space, which will come in the third or fourth lecture, but please take it from me that we have started using certain lingos which will be gradually defined. So, you gradually get habituated in speaking a lingo, and once you start speaking the lingo, you gradually start feeling comfortable when that concept comes, you already have certain examples on which you can map those ideas to those examples and see how they tally. That is an important way of doing mathematics. So, here this result holds true, of course. Now, WV is not equal to VW, here the symmetry is not maintained, but a conjugate symmetry is maintained. I worked it out, it is very simple, that if you have VW, you can define it like this, and if you have so if you take VW bar, you define the VW, which is V1 bar, W1 bar, V2 bar, W2 bar, and you take the whole conjugate. Now, properties of the conjugate of a complex number, you will get this one, that you take the sum of the separate conjugates, and then the product of the conjugate is conjugate, or conjugate of the product is of two complex number is the product of the conjugates, and conjugate of the conjugate is the complex number itself, and using that you get back this. Here you of course use commutativity of complex numbers, and that is it. So, there are other properties also, that is, if you take lambda here and then and multiply with the right part, then lambda would come out, because you do not take conjugates on V on the second vector. But if you take lambda on the first, multiply the first vector with lambda, a scalar multiplication. So, lambda is a element in C of course, then a conjugate will come out, because when you write the inner product you will write lambda bar W1 bar. So, lambda bar would come out and this would remain same, right. So, let us prove, though we are proving the second fact, which is this one, that the bar comes out. So, here you see the bar comes out and this is what you have. So, you can prove the remaining ones for practice. You can even write them in terms of complex numbers and be more detailed, but you do not have to. So, when writing them as xi plus iyi types, you do not have to, just use the properties of complex number. So, what last part was a detour, a kind of entertainment lecture, which you need not bother especially with the economic students, but even other viewers, those who are physics students can have some help here, physics or some other thing. Even mathematics students can just sit down and enjoy, because they should be able to handle many other things apart from these things. But they can look at inner product in a much more general way. It is called that is called a kind of valuation of a vector space over a given field. So, just forget all those terms now. So, you know about how to do inner products for real vectors, how to do inner products for complex vectors, and you have some properties, and that would allow us to now get into a situation in the next class where we stack up a vector, couple of vectors, column vectors, and form an array, and we call the matrix, and we will see how useful that concept is and how far reaching its effect and how far reaching is its power. So, with this I close the second part of the class. Thank you.